The evolution of RISC-V processor verification, open standards and verification IP. Abstract. The open hardware group verification task group have been a pioneer in the development of the methodologies and verification collateral for RISC-V processor verification. Since 2019, the members have been worked together to develop CORE-V-VERIF, a UVM environment for the verification of RISC-V or processor cores. Over this period of time, the CORE-V-VERIF environment has evolved as a new processor verification project introduced new challenges and running from the previous project led to the development of the new approaches. With each generation of the CORE-V-VERIF environment has improved to become more robust and more reusable, and the alternative better at finding RTL bugs. The current generation uses RISC-V processor verification IP enabled by the open standard RISC-V verification interface RVVI to realize a comprehensive verification methodology that encompasses asynchronous preferred events that occur randomly during program execution. This paper will describe the evolution of RISC-V processor verification methodology using CORE-V-VERIF as a case study. Readers will learn a proven approach to the RISC-V processor verification that can be accessed through an open source example. Readers who are already familiar with the CORE-V verification may choose to skip ahead of the system of third generation verification environment to learn about the latest development. Introduction. So the popularity of the RISC-V instruction set architecture ISA for microprocessor is growing, and with it is the need for and interest in processor-specific design verification techniques. And one of the main contributors to the evolution of RISC-V processor DV is Open Hardware Group's verification task group. The focus on this group is to ensure that the CORE-V family of the open source RISC-V processors cores is verified to industry standards so that anyone who adopted these cores can feel the confidence that they are ready for silicon. In addition, for any developers that are modified or extended to the open source core IP, availability of the test bench infrastructure provide the basis for the verification of the new enhancement. While industry standard verification techniques such as constraint random generation and functional coverage closure were applied, so the verification task group has been a pioneer in developing RISC-V specific verification methodologies and test best practices, and in turn making these available to wider community. The Open Hardware Group and each member company is supporting an ongoing effort to develop and maintain a portfolio of RISC-V compliant cores collectively known as the CORE-V family. The verification environment used to verify the CORE-V core is known as CORE-V-VERIF, and it too is an open source artifact available in GitHub. The leader is invited to review the CORE-V-VERIF Quick Start Guide and for information about running simulations on CORE-V core under the CORE-V-VERIF environment. So the first and the second generation of the open source group's CORE-V-VERIF utilize the C reference model for a processor embodied in a UVM test bench. The reference model and the device under test DUT were run in a lockstep, each executing the same program, while the test bench compared the internal state of the two at the entire retirement of every instruction. This becomes known as the step and compare methodology, used together with a random instruction stream generator and UVM agent providing preferred stimulus, such as interrupt. It was an effective method of achieving the verification closure for CV32E40X RISC-V processor RTL. Although successful, the time and the human effort requirement to develop the first and second generation CORE-V-VERIF environment and achieved verification closure was high. The OpenHW group was developing ambitious plans to achieve the same level of the verification for the RISC-V additional RISC-V cores, and it was clear a more efficient methodology was required. The experiments with this verification project led to observation that some components should be common to all RISC-V processor test benches, and common components should conform to standard interface. This led to the development of RVVI as the RISC-V verification infrastructure. In turn, the ability of the standard interfaces made it possible to develop verification IP that implement these common components. And these innovations have contributed to the third generation of the CORE-V verification environment, which is in use today with multiple RISC-V core development. The following section will provide greater detail into the evolution of the CORE-V-VERIF environment in RISC-V verification methodology. The first and second generation CORE-V verification environment will be described along with the highlights and shortcomings of each. Next, the RISC-V verification interface RVVI will be described in detail, with the explanation of how it starts to address the shortcomings mentioned previously. The evolution continues to the introduction of verification IP to promote reuse and improve in the checking and gain further efficiency. Finally, the present day third generation, the CORE-V verification environment will be shown to demonstrate the successful application of these techniques and provide context for future work. The first generation CORE-V VERIF environment. The OpenHW group develops the open source designer verification IP centered the CORE-V family of the RISC-V cores and related IP, and the verification environment for the CORE-V cores are maintained as an open source artifact in the CORE-V VERIF GitHub repository. The first generation of CORE-V VERIF environment is illustrated in Figure 1 below. The SystemVerilog test bench with the UVM test benches. Figure 1 is the first generation of CORE-V verification environment. So, as illustrated in Figure 1, a common strategy in simulation-based verification is to integrate the design under test, DUT, and a reference model in a test bench and compare the state of the DUT and the RM at specific times during the simulation. In process core verification, the state variables from the interest will typically be the program counter, general purpose register, GPRs, and the process and control and status register, CSRs. The most natural time to compare the state of the reference model and DUT is when an instruction has been retired. That is, execution of instruction has completed and the values of the PC and GPRs and the CSR have been updated to reflect the effect of the instruction. Conceptually, the theory of operations of such a test bench is as follows. Both DUT and a reference model execute the same problem. Note that the CORE-V VERIF test bench, these programs can be manually written by a human or generated by a random instruction stream generate, not shown in Figure 1. So next, second one is non-programmatic interrupt to a normal program flow, such as external interrupt and a debug request are sent to both DUT and a reference model. And the non-programmatic interrupt to normal program flow are termed asynchronous event in remainder of this document. As each instruction retires, the state variables of DUT and reference models are compared. Mismatches are reported as errors. This method is known as step and compare. In a typical process core, the state of the PC, GPR, and CSRs are not accessible as top-level I/O port. Additionally, due to the implementation of the processor's internal pipeline, the values of these variables may be updated at different clock cycles as instructions are executed. Exposing the state of the DUT and a test bench is the job of the module called tracer. So an important consideration of the tracer is ensuring that all aspects of the core state are presented in a way that allows the consumer of tracer output to attribute the state to the specific instruction. In the first generation test bench, the tracer used was an ad-hoc behavior model bound to a RTL exposing the all processor state such as GPR and CP, PC, and CSR values. This tracer lacked the document interface and required frequent changes in both tracer itself and step and compare test bench logic. The design and implementation of reference model is a key consideration for this test bench architecture. An instruction set simulator is often used as a reference model, often developed and/or used by different software development teams, as an ISS can ISS can be custom built in-house and commercial product or available as an open source artifact. The CORE-V-VERIF environment uses Imperas OVP simulation as the reference model for the embedded class cores. Using an ISS significantly reduces the development effort of the RTL test bench. This was the strategy employed by the first generation CORE-V-VERIF environment. However, as we will see, it came with significant challenges, and the remainder of this paper will discuss these and introduce a strategy for addressing them. The most obvious problem encountered when using an ISS as a reference model is caused by the different abstraction levels of the ISS and DUT. The majority of the DUTs are simulated at the register transfer level, which by definition is a clock cycle accurate description of a hardware logic in which time is modeled as clock event. This is in contrast to transaction level model in which time is modeled as the transaction cycles. In our case, an ISS of a processor core models time in terms of instruction. So while the RTL model of a core may take multiple clock cycles to execute an instruction, depending on the instruction fetch bus timing, so the specific instruction being executed or the state of the internal pipeline. So an ISS will usually execute an instruction in a single instruction cycle because the cycle timing of the physical interfaces to memory and the operation of a core pipeline are abstracted away. So the abstraction inherent in an ISS is a powerful modeling technique, and it is highly effective at producing predictions of the core states when executing a series of instructions which are not subject to an asynchronous event such as an interrupt. Nonetheless, a method must be found to maintain synchronization between the ISS, which operates in terms of instruction cycles, and the DUT, and which operates in terms of clock cycles. The method used by a CORE-V-VERIF to maintain this synchronization is called the step and compare. A second problem when using an ISS as a reference model is the timing of the side effect. An instruction is said to have a side effect if it updates one or more state variables which are not explicitly part of the instruction. For example, the CSR mean to read is updated each time. In most cases, the side effects are easy to predict. In other cases, particularly in the event of the synchronous and asynchronous interrupt, the time of the side effect in the ISS may differ from the RTL. The step and compare architecture. Reference A documents the original step and compare method used in the first generation of CORE-V-VERIF test benches. An ISS is used as a reference model is kept in sync with the RTL by running the RTL clock until an instruction is retired, at which point the RTL clock is gapped The reference model is allowed to run until it retires an instruction. The test bench then compares the prediction processor state from the reference model, the actual processor state from the RTL. This process repeats until the last instruction is retired and compared. So this technique works very well in the absence of external asynchronous events such as debugging request, interrupt, and memory access delays and memory bus errors. In the first generation of the CORE-V-VERIF, the ISS and RTL were connected to the same interrupt and debug request input. Due to the clocking system enforced by the step-by-step and compare logic, the ISS would always see this external event as being synchronous to the start of the instruction. Due to the internal microarchitecture of the RTL, these external event may or may not be seen as occurring before or after the start of the same instruction. So this would inevitably result in differences in predicted and actual processor states, and a false negative comparison would result. So the make matters worse. Each asynchronous event needed to be handled as a unique event with a core-specific code in a test bench to properly handle the behavior and side effect of these asynchronous events. This made the test bench buggy, prone to the false negative, and difficult to maintain. In response to this, a second generation of a step and compare was developed to build upon and fix many issues with the first generation while maintaining the same verification effectiveness. For the purpose of this discussion, the most purposeful improvement were to formalize the tracer interface definition. This is the second generation CORE-V verification environment. So figure 2 is the second generation CORE-V verification UVM environment. Figure 2 is above illustrates the changes implemented to create a second generation UVM environment. So the ad-hoc tracer used in the first generation is replaced by a tracer conforming an interface extended from the RVVI specification. So the new simplified second generation step and compare 2.0 is developed. So the asynchronous events such as interrupt and debug requests are connected to the core RTL device under test, but not the ISS. Each point from the above list is significant and will be discussed further below. The CORE-V tracer using RVVI plus extension. In the first generation test bench, monitoring of a processor activity was enabled by a specific purpose tracer. The tracer was bound to the RTL exposing all processor states such as GPR, PC, and CSR values. This tracer was difficult to maintain and implemented with an ad-hoc interface, requiring and customized frequent changes in the step and compare implementation. So to address the issues with the ad-hoc tracer, the RISC-V formal interface RVVI specification was adapted to define the requirement for the processor tracer. As much as was practical, the RVVI was followed verbatim and with an update for extra requirement introduced by its usage in step and compare. The detail of the specific CORE-V RVVI implementation extension used in it captures in the user manual of the CV32E40X, an RV32 process core targeting embedded application. So the CORE-V tracer probes in the internal design of the core to perform the following functions: unambiguously identify the instruction retirement, the ambiguous reporting both synchronous traps and asynchronous exception, interrupt, and debug request. Expose the state of the core, PC, GPR, and CSRs. Depending on the complexity of the core pipeline, the logic required to implement the CORE-V tracer ranges from the trivial to complex. The simplified CORE-V tracer, and it is typically implemented as a behavior module that is bound using a SystemVerilog bind into an RTL model. This simplified implementation because the coding is not constrained by synthesis requirement and can be maintained as one or more source files outside the RTL sources. A significant benefit of having a tracer interface specification is that it provides a well-defined blueprint of the requirements of a complete tracer. This is more impactful than it at first appears. It can be difficult to fully specify the requirement of a tracer a priori without first having the experience of using the tracer that does not fully fit your needs. It's often the case that such a requirement can only be fully understood after several cycles of trial and error. This experience is what eventually led to a new open standard RVVI specification. So small sections, handling asynchronous events with a CORE-V second generation tracer. In the first generation of a CORE-V-VERIF, the reference model saw asynchronous events such as interrupt and debug requests simultaneously with the RTL model. Due to the differences in timing, this could mean that RTL and reference model would take the interrupt on different instructions. This placed a burden of a step and compare logic in the test bench to ensure that a reference model would take the interrupt on the same instruction as the RTL. In the second generation of the CORE-V-VERIF, the reference model is connected to a synchronous event. Thus, on its own, the reference model cannot determine when interrupt to normal program flow occur, such as external interrupt and external debug request. So the tracer monitors and reports those events, and thus the step and compare 2.0 logic can be used to inform the reference model to interrupt normal program flow, to maintain the processor state lock step with the duty. This is possible because the tracer interface is explicitly defined to indicate when this information is presented to the reference model, and all of the information required by reference model is provided at the time the RTL retires an instruction. For an example, consider what happens when a debug request is asserted. The CORE-V tracer interface defines two signals RVFI_DBG and RVFI_DBG_mode that are valid when an instruction is retired. So together, these two signals indicate whether the core executed the entire instruction in a debug mode and the first instruction after entering debug, and RVFI_DBG contains the debug codes. In addition to providing this information, the CORE-V tracer specified clear rules for how debug entry is recognized. So, debug entry is seen by the tracer interface as happening between the instruction. This means that neither the last instruction before the debug entry nor the first instruction of the debug handler will signal any direct side effect. The first instruction of a handler will, however, show the resulting state caused by these side effects. For example, the CSR, the RMask, R data signals will show the updated values. PC_R data will be an debug handler address, and etc. The CORE-V tracer interface has similarly comprehensive and rigorous definition of how an interrupt is signals and how side effects are modeled. This information greatly simplifies the step and compare logic required to keep the RTL and ISS state in sync. However, this methodology left a serious verification hole. The reference model was not able to provide independent verification of the duty response to asynchronous event. For example, in a case where multiple instructions are enabled and pending, it was unenabled to verify the correct one by priority was taken. It simply mirrored the actions of the deity. Checking this type of the behavior was left to other test components, given the difficulty of validating the responses to randomly generated asynchronous events, so this checking was often incomplete. This serious deficiency was addressed the third generation of CORE-V-verified environment. RVVI, the RISC-V verification interface. The work of the OpenHW group VTG on the first and second generation of CORE-V-VERIF environment led to the observation of the certain component should be common to all RISC-V processor verification environments, and a common component should be accessible through the standard interfaces. So these interfaces have now been formalized in RVVI, the open and evolving standard for functional verification of the RISC-V processors. The two major components of RVVI will be discussed: RVVI-TRACE and RVVI-API. So RVVI-TRACE, a common component that benefits from the standard interface of the previously discussed tracer. Every RISC-V processor under the test needs a tracer module in order to extract internal state information required for effective verification. While the implementation of the tracer is specific to each processor's microarchitecture, the requirement for the information that a tracer should provide are common and are defined by the needs of the test bench. These requirements led to a creation of the RVVI-TRACE specification. RVVI-TRACE is specified as a SystemVerilog interface that connects the processor under test with the test bench. When determining what the standard interface for a tracer should look like, it was natural to study former interfaces being used in a processor verification and see if they were appropriate for dynamic simulation-based verification. It was clear that RVFI did not meet the needs of functional verification, as it was designed for formal verification and heavily extended and modified for CORE-V-VERIF, the CORE-V-VERIF at the environment. The CORE-V extension to it were inefficient for a standard interface, as they were specific requirements of CV32E40 cores and did not anticipate the needs of the full set of the RISC-V ISA variations. For example, RVFI did not have a method for over-signaling more than one register change side effect for instruction environment. So something which does happen in a RISC-V VGC extension. Today, the RVVI-TRACE interface addresses this and the other issues with RVFI and can be seen as a natural evolution and extension into dynamic verification of RVFI. The another key feature of the RVVI-TRACE is a mechanism for handling the asynchronous input to the processor. The RVVI-TRACE contains a SystemVerilog queue that is used to store multiple net changes that occur during the interrupt between the instruction requirements, as well as when those changes occurred. This information is now available to the reference model or checker for validation of the processor responses to these events. So for the CORE-V-VERIF environment, the benefits of adopting RVVI-TRACE further extend the benefits realized by the development of the initial CORE-V-TRACE interface. There is still existing benefit of the knowing upfront what are the requirements for an effective tracer and being able to clearly communicate these to the design team. There is additional benefit of having an interface to support the full suite of RISC-V ISA subsets so there is no need to modify it between the different a processor project. This in turn permits the use of any component that is client of the RVVI-TRACE interface. So what is RVVI API? Another component required for comprehensive RISC-V processor verification is a behavior reference model of the processor. The reference model provides an independent presentation of the processor's internal state. It is subject to the same configuration and initial conditions and execute the same program as the duty. The model should have the ability to run into lockstep with the duty so that the two stages can be continuously compared and clocks can be identified at the time they occur. In addition to the reference model, a processor verification environment needs a component to perform a comparison between the model and the duty to keep track of any mismatches in state. This set of the requirements led to a development of RVVI API. A set of functions must be implemented in the processor verification IP and supporting the test bench component in order to comprehensively check the behavior of the RISC-V processor under test. The diagram of the figure 3 below illustrates a canonical RISC-V processor verification environment using RVVI and RVVI complement processor verification IP. So this is the figure 3, the test bench for advanced RISC-V processor verification using RVVI. And the instruction of the RVVI API into CORE-V-VERIF have addressed some of the shortcomings and issues encountered with the previous step and compare environment. One of these areas is the configuration of RISC-V verification IP and processor reference model. RVVI API specifies the functions figure 4 to configure the specific memory regions and registers and register fields as volatile. The volatile control and status registers, CSRs, and memory regions are those changes asynchronously to the program execution, and they often require a cycle-accurate representation of a processor to model accurately. An example of a volatile CSR is a counter that is increments every clock cycle. An example of a volatile memory location is the address space used by a memory mapped preferer. It's important to note that the reference models used for RISC-V processor verification are the instruction accurate and not cycle accurate. So these are architectural models for adapt model processor behavior, but do not model microarchitecture details such as the processor's pipeline. In the first and second generation of the CORE-V-VERIF environment, the verification IP and processor reference model had no notion of volatility. It was up to the step and compare logic to maintain a list of the register comparison, to discard, and to populate the correct register values in the reference model. This ensures that the test program will run as expected. The figure 4 is RVVI API volatile functions. This figure is the third generation CORE-V-VERIF environment. The figure 5 is the third generation CORE-V-VERIF environment. The figure 5 above illustrates the changes implemented to create the third and current generation UVM environment. The CORE-V tracer has been replaced with the RVVI compliant tracer, so the Imperas reference model has been replaced with the ImperasDV verification VIP that incorporates the reference model, so that the step and compare logic has been eliminated. The benefit of adopting the RVVI compliant tracer have been discussed with the previous sections. At the time of the writing, so that the migration from the CORE-V's use of the RVFI with extension to RVVI is an ongoing activity. The most impactful change has has been replacement of the reference model and step and compare logic with the piece of verification IP. The ImperasDV VIP encapsulated the reference model of the target processor and implements the functions specified by RVVI API. It performed the internal state comparisons between the reference model and the DUT using information from the RVVI-TRACE interface and keeps the track of those results in an internal scoreboard. So this eliminates the need for error prone and the complex step and compare logic being hand-coded in the test bench. Since these asynchronous events are now communicated with the VIP using RVVI-TRACE, the processor responses to these can now be independently validated. So the following section contains an explanation example of how an architecture reference model can be utilized to provide validation of the processor handling of asynchronous inputs such as interrupt and halt request. Handling the asynchronous event with ImperasDV. As previously discussed, one of the most challenging tasks in the processor verification is maintaining a consistent view of the program execution between architectural and microarchitectural representation. Using this prediction and validation from the architectural model in order to verify an RTL implementation is highly desirable, but it is challenging to provide useful data and useful predictive behavior. So let's consider a very simple example how to determine the correct point during program execution to apply an external asynchronous event such as an interrupt. When applying the interrupt to an architectural representation, it can be taken immediately if enabled upon a receive, causing the processor to take an inception and begin execution at whatever is defined as the interrupt handling address. In a microarchitecture implementation, it is not so simple. For example, the interrupt input logic may contain oversampling to ensure the interrupt logic is observed to be inactive and clock cycles. Once the logic has decided that an interrupt is inactive, it then has to be merged into instruction pipeline at an appropriate time. It may be decided that it is wasteful to discard a complex instruction which executed for 32 cycles if it has already been executing for 28 of those. It's better to take an interrupt latency penalty of 4 cycles rather than discard and lose 28 cycles. This is one of the many microarchitecture performance decisions that must be considered in order to ensure the best throughput versus responsiveness. Making sure the architectural models match it, these and many other similar scenarios can be very difficult. Consider a simple problem of staircase waveform of interrupt shown in figure 6 below. This is where the interrupt lines ramp up over times on each clock edge. The reference model will receive these net changes as said, but it is impossible for an architectural model to know which interrupt was highest priority at the exact time the DUT would have sampled and propagated that particular value. This leads to a set of legal scenarios, any of which may be executed by the DUT. So it is a task of the microarchitectural reference to determine what this set of legal scenario can be, and to ensure that the path the DUT has chosen belong to that set. In the scenario above, there are 9 legal outcomes, taking any of the interrupt 0 to 7 and entering into interrupt service routine, or not taking the interrupt or at all the continuing with the normal program execution. This automatic analysis of legal scenarios recently revealed a bug of an OpenHW group CV32E40X processor core. So it involved the following sequence of events. A set of randomly generated external interrupt signals have been propagating into the local interrupt of the processor core. So these interrupts are masked by the two levels of logic. Firstly, there is MIE, Machine Interrupt Enable CSR, and the Global Interrupt Enable field of the M status register, mStatus.MIE. So an interrupt is detected by evaluating the following expression, IRQ, the figure 7 expression for the detecting a valid interrupt. So the expression stated for an IRQ to be independent and enabling, we must have the equivalent positional hits true in both MIE and MIP. And the global interrupt enabled mStatus.MIE must also be true. The upper 16 MI bits local interrupt 0-15 are direct representation of the interrupt pins on core, bearing in mind there is a clock to logic to sample these pins. When the that was the instruction. MRET instruction is executed. The expression in figure 7 evaluates true. However, since the interrupt pins have been toggling during the interrupt since the previous instruction was retired, it is unknown which interrupt should correctly be active, so that the analysis engine must identify the legal possibility based on a signal transition as received via RVVI-TRACE and the current status of the processor, and to ensure the DUT has executed one of these. So in this instance, the DUT actually did not serve as interrupt. It executed the break instruction and entered the debug mode instead. Since these did not match any of legal scenarios, an error was flagged. This bug is now captured in OpenHW group GitHub issue taker here. The future work. The CORE-V-VERIF verification environment continues to evolve both in response to new requirements for the extending roadmap of new cores and to ongoing learnings from the current and previous verification efforts. An upcoming enhancement to the environment will involve automated generation of functional coverage of retired instruction. This is enabled by a common tracer interface, RVVI, and supports all information required for instruction coverage by the standard definition of the RISC-V ISA. Summary. The OpenHW Group Verification Task Group has been a pioneer in the field of the RISC-V processor verification. Through the CORE-V-VERIF environment, we have employed the different approaches and evaluated the merits and more usable, more efficient, and ultimately better at finding RTL bugs. The current generation of the CORE-V-VERIF uses RISC-V processor verification IP enabled by the RVVI realized comprehensive verification methodology that encompasses asynchronous preferred event that occurs randomly during the program execute. This is the state-of-the-art methodology at present. However, the verification task group members are highly motivated to continue to innovate the advanced practice of the RISC-V processor verification. Okay, acknowledgement and the references. Today I read this paper about the RISC-V, the evolution of RISC-V processor verification, open standards and verification IP, from the DVCON2023. Thank you for your time. See you next time.